We have three speakers, great speakers this morning, to talk about manganese in water. Dr. Deanna Scher is an epidemiologist in the Environmental Health Division at MDH, and she has been in that capacity since 2007. She's worked on a variety of studies to assess exposures to and health impacts from environmental contaminants. And she is a state-appointed member of MDH Institutional Review Board and the MDA's Pesticide Management Plan Committee. She also currently serves as chair of the EPA Children's Health Protection Advisory Committee. Dr. Klos has been a scientist with the Health Risk Assessment Unit at MDH since 2014. She earned her PhD at in Houston, Texas, and eventually went on to study DNA damage to cancer stem cells at the University of Wisconsin at Madison. She is currently developing guidance for contaminants found in Minnesota groundwater. And it is a real pleasure to welcome as one of our speakers, Dr. Helen Goeden, who I have known in some capacity since our halcyon days of working in the Superfund cleanup area at the MPCA many years ago. And after leaving those halcyon days at the MPCA, Helen left to become toxicologist and risk assessor at MDA, and she has been developing and improving risk assessment methods and policies. For the past 20 years, she has worked at MDH, where she led efforts to expand methods used for deriving human health-based drinking water guidance to include multiple exposure durations and to explicitly consider sensitive or more highly exposed populations. It is a real pleasure to welcome all of our three speakers today, and they're going to be talking this morning about tap water and powdered infant formula, a risk assessment of neurologic harm from total manganese exposure. I have been looking forward to this talk all week, and I believe, Chris, you're going to be starting us off with the presentation. Why don't you take it away and run with it?
Okay, thank you, Mark. Oh, by the way, our supervisor just kind of texted me and asked for the correct link. I think I just sent it to her, so we'll see if she gets in. But yeah,
I'll be watching my email too, and if people have a question about the link, I'll try to correct my mistake by and by.
Okay, well, Helen, Deanna, and I would like to thank you all for letting us share our morning with you. And so today we're just going to talk to you about a combination of studies that we published in Environmental Health Perspectives this year. Next slide. So we'll start by giving a background on manganese, and then we'll tell you how the pieces of the study fit together. And these pieces are a formula study that we did in infants, water studies, and then a risk assessment that we used to combine the formula and water studies together. So then we'll just briefly present some conclusions that we have, and then we'll talk about MDH's response plan for citizens that have high levels of manganese in their water. Okay, Helen. So we know that manganese is a naturally occurring element. So it's in our rocks, it's in our water, it's in our soil. Because it's in our soil, it's in our plants. So we get a lot of manganese just by eating food. And so food that has high level of manganese includes your oatmeals, your nuts. Tea has a lot of manganese in it. So we got an email now. Todd Johnson's having problems getting in. So just an FYI there. These are popping up on my screen. So anyways, we get enough manganese in our diets to protect our health. And actually manganese is important for our health. So it's involved in metabolism and bone formation, and we need enough to stay healthy. It's also a component of a lot of proteins and enzymes. So it's an essential nutrient that we all need. We don't make it, but we need it from what we eat. However, manganese is neurotoxic at high levels. So therefore, if you see the chart on the left-hand side of your screen, this is from the Institute of Medicine in 2001, and the age is on the left-hand side. And then we have adequate daily intakes of manganese. And as you can see, as you grow older, the adequate daily intake increases. There's also upper limits that the Institute of Medicine put on these intake rates. And as you can see, for infants, there's question marks just because there's not enough data out there right now to know exactly what level you cross over where it becomes toxic. And we know that, again, that manganese is neurotoxic at high levels. It's more easily absorbed when it's in water, and infants are at the greatest risk of overexposure because they drink the most water. So if you look at the chart on the right-hand side, the graph, the blue bars are the mean water intake, and the orange bars are your 95th percentile water intake rates. And the first two columns, those are your infants under 3 months. So you can see compared with older children and adults, it's the infants that drink the most amount of water. So manganese is more easily absorbed when it's in water. Infants are rapidly developing. They also absorb more manganese and they eliminate less of it. So, and combined with that high fluid intake rates, it's infants that are the sensitive population for manganese overexposure. Okay, Helen.
Hi, this is Deanna. I wanted to give a little bit of background on manganese in drinking water because I think some of the regulatory history helps put our risk assessment in context. So like Chris said, it's common in water. It tends to be higher in groundwater. So in 1979, EPA established a non-regulatory secondary maximum contaminant level for manganese of 50 micrograms per liter to enhance consumer acceptance of the water due to its bitter metallic taste and staining issues. And a common assumption is that a noticeable unpleasant taste above the secondary MCL will trigger a public water system to treat for manganese or will effectively dissuade people from using the water. However, there's a lot of confusion about what level of manganese will act as a deterrent to drinking or will incentivize public water systems or residents to treat water to remove manganese. So manganese was on the first contaminant candidate list, CCL1, for EPA's, assessment of contaminants in drinking water and whether they need to be regulated. So to try to determine whether regulation is needed for manganese, EPA established a health reference level of 300 micrograms per liter for which to compare to drinking water concentrations. So if EPA is seeing that drinking water concentrations aren't above this health reference level, that's an indication it does not need to be regulated. However, the health reference level that they chose was based on an adult drinking the water, so an adult body weight, an adult drinking water consumption rate, and a standard assumption that drinking water contributes 20% to total adult exposure, which does not apply to an infant. The reference dose that they used, the estimate of daily oral exposure that's likely to be without risk of harm, was not based on oral toxicity studies in animals, which is typically the case, but rather the upper end of the range of manganese intake from an adult Western diet. EPA did apply a modifying factor of 3x to address concerns related to increased infant vulnerability and exposure and potentially higher absorption from water compared to diet. But in 2003, EPA's ultimate regulatory determination was that manganese did not need to be regulated. In 2004, EPA did issue a health advisory, and this was based on that same adult-based health reference level. EPA did advise that infants shouldn't be given drinking water above the health advisory level for more than 10 days. But EPA did not identify a water concentration that would be safe for infants to consume for greater than 10 days. So that was really a knowledge gap of what level is safe for infants to consume. There has been a lot of recent study of manganese from the epi side, from the tox side. And so recognizing that there's new information, EPA decided to reassess manganese again to see if it should be regulated. So it was included in UCMR 4, Unregulated Contaminants Monitoring Rule. So EPA did sample finished water from community water systems from 2018 to 2020 as part of that effort. Now, at the state level, MDH develops and establishes rules for contaminants in groundwater. And in 2011, MDH reviewed and published a short-term health-based guidance value of 100 micrograms per liter for manganese, compared to that 300 microgram per liter health advisory. And the MDH value is based on neurobehavioral effects in neonatal rats compared to that adult-based dietary intake basis that EPA used. And Helen will discuss the MDH guidance value further in the presentation. So, like I said, it's common in water. And in 2019, USGS put out a study that provided US groundwater concentrations. And you can see from the map here that manganese is elevated across the United States. It's not just a Minnesota specific issue. And they found that 24% of groundwater samples exceeded MDH's health-based guidance value of 100 micrograms per liter, and 13% of samples exceeded EPA's health advisory. And so this is really concerning since we know 75% of Minnesota residents rely on groundwater for drinking water. Next slide. So, so there has been activity at the state level, and looking specifically at the situation in Minnesota after MDH Health Risk Assessment Unit published that short-term guidance value. The MDH Source Water Protection section published an initial assessment of manganese in groundwater, and they relied on data from MDH, PCA, USGS, the Minnesota Geological Survey, DNR, and local government sources to look more closely at what's happening in Minnesota with manganese. And the basic conclusion was that 50% of the groundwater samples were above the health-based guidance value, and 22% were above EPA's health advisory. And this map just shows where some lower concentrations are seen in southeast Minnesota. You see some much higher concentrations in southwest Minnesota. So based on this knowledge, a white paper was published in 2015 from Minnesota Groundwater Association to facilitate awareness building about the health effects of manganese in drinking water, the availability of the new health-based drinking water guidance from MDH, and it's trying to spread awareness about the spatial distribution of manganese in groundwater and effective ways to reduce manganese. Because this was kind of a big deal. I mean, if 50% of private wells are above our guidance value, I mean, that's way more than we see for arsenic exceedances or nitrate exceedances. So there was still a lot of knowledge gaps out there. We know it's an issue in Minnesota groundwater, but what does this exactly mean for drinking water? Are people on public water systems and private wells actually drinking water with manganese at concentrations above our guidance value? Are public water systems trying to achieve that secondary MCL value of 50 micrograms per liter? And how much does infant formula then contribute to a bottle-fed baby's total exposure? Next slide.
Right, so this is Chris again. So this was one of the knowledge gaps, is how much actually is in infant formula. So we knew that breast milk levels are relatively low. So they're usually under 15 micrograms per liter. And from talking with the FDA, we knew that manganese is purposefully added into formula because it's an essential nutrient. It has to be added, and they put minimum requirement of 34 micrograms per liter into the formulas, but there's no maximum. A third thing we need to know is that our health-based guidance value is based in part on older studies that rely upon the label concentrations. So one of the things we wanted to find out is exactly how much manganese is in a variety of different infant formulas. Next slide, please. So this is kind of where all these pieces fit together. So you can see in the upper left-hand square, one of our studies was to analyze manganese levels in powdered infant formula. And then we also used information from MDH from a study that evaluated manganese levels in Minnesota's community public water systems. And then we combine these together, as you can see with the picture of the baby, for a risk assessment that we did for total exposure to formula-fed infants. And then along with the information, the data that came from the community public water systems, a survey was done to also find out whether high levels of manganese affected the taste of the water and whether or not people either fixed their water or continued to drink it. Okay, so next slide. Okay, so now we're going to talk about the formula study that we did. So how much manganese is in powdered formula? Okay, next slide, Helen. So we ended up ordering from Target 27 different infant formulas. And when we picked the different formulas, we wanted to make sure that we had the top 10 that were sold in the United States. We wanted a variety of suppliers, so we chose from the major brands, the big three, Enfamil, Gerber, and Similac. We also wanted store brands represented, so we bought Target's Up and Up. And then we wanted to include organic brands, so we had Earth's Best and The Honest Company. And then we wanted to make sure that we had the different bases of formula. So we made sure that there was cow's milk, soy milk, and then an amino acid representative. And actually the amino acid formula came from Walgreens. Okay, next slide. So we went to the public health lab, the MDH public health lab, and we used purified water and we mixed formula according to the label instructions. And we did 2 different rounds. It was the same formula, but 2 different rounds with 2 different people. And that simulated 2 different parents, you know, getting up in the middle of the night to make formula. And then once we mixed all these, then we gave them to the public health lab for analysis. Okay, next slide. And so what was surprising was that the manganese levels in these formulas fell out based on what base was used. So if you look at the blue dots, these are all cow's milk based formulas. The red triangles are soy based, and then the lone amino acid formula that we had is that green diamond up at the top. So as you can see, as you go up the graph, that signifies the average manganese concentration. So basically it was the soy and the amino acid concentration that, or the amino acid base that had the highest amount of manganese. All right, next slide, please. Okay, and this is just interesting. In this graph, we compared what we measured in the lab versus what was labeled on the jars and cans. So as you can see, in every single case, what we measured, the amount of manganese that we measured was higher than what was labeled. And this went anywhere from just over 1, like 1.3, up to almost 5 times higher concentration in the powdered formula than what is on the label. Okay, next slide.
So that's what we did for formula. And now I'm going to talk about some of the water analyses that we did to try to fill some knowledge gaps about drinking water. Next slide. So to try to understand what water is actually being received by people on public water systems, we looked at what community water system data we had. And fortunately, MDH had done a study called the General Water Chemistry Project that was that collected samples from 2010 to 2014 to look at baseline chemistry data for community water systems statewide. So this was a really robust source of data for an unregulated contaminant like manganese. So as part of that project, I had raw water results, so from wells or surface water intakes, and finished water results from the entry points to the distribution system after treatment. 41% of the systems only had raw water results, however. Another data source was EPA's UCMAR4 monitoring that was conducted later, 2018 to 2020. That was just finished water. So if there were UCMAR4 results for a system, I selected those over the earlier study results. I tried to create one result per system. We ended up having almost 3,000 samples from both MDH monitoring and UCMR monitoring. So the within system results were averaged to create one result per system. And there were some systems that only had raw water results. So in those cases, I considered the treatment technologies that the system had to determine if the raw water represents finished water or if there was some type of treatment that would likely remove the manganese, such as oxidation, physical separation, absorption, oxidation, biological filtration, or precipitative softening. Next slide. So looking at the results for community water systems, what we found was that the average concentration of the system was higher than the MDH health-based guidance value in 27% of community water systems. And those 20% of systems are estimated to serve 345,000 people. We found that 10% of community water systems had an average concentration of manganese higher than the EPA health advisory of 300 micrograms per liter. We did see that manganese concentration tended to increase as the system size decreased. So this raises some environmental health equity concerns. So we see in the table the system size increasing as you go down, and you can see how much the median and the upper percentiles decrease as the system size increases. Now, it's important to point out that UCMR4 sampling took place at all large community water systems, greater than 10,000 people, but only 1.5% of the small to medium systems to provide a nationally representative sample of community water systems. But you see they sampled very few of these small to medium systems where you're seeing these elevated manganese concentrations. Next slide. So the other aspect of this we wanted to look at was whether the aesthetic issues associated with manganese act as a deterrent or not to drinking it. So even if a community water system provides that water with elevated manganese, maybe people are treating it at their home. So I think Vanessa DeMuth actually previously presented in a water issue seminar on this study that we did jointly, looking at manganese in private wells in Inver Grove Heights. But I'm just going to talk today about one aspect of that study was related to the household survey we did. So this was back in 2015. We partnered with Dakota County to do this private well water quality studies in Inver Grove Heights, where we suspected there was a variable levels of manganese in groundwater. We enrolled 274 households, and Dakota County staff collected a well water sample of the unfiltered, untreated water from an outside spigot at each home and tested for several well water quality indicators and contaminants. And we did not we did not tell participants that we were uniquely interested in manganese for this study. At the same time that the water was collected, an adult member of the household completed an online survey about water treatment devices in the home, their water use, and concerns about well water quality. And they completed the survey prior to any receiving any water quality results. There was also a second phase of the study where households that were identified as having a manganese concentration in their outdoor spigot above 100 micrograms per liter were invited to participate in free follow-up sampling of manganese from an inside tap after the water had gone through any treatment devices used in the home. Next slide. So what we found was that 71% of the homes had an outdoor untreated result from their well of over our health-based guidance value, and 56% had a well water result above the EPA health advisory. We did also see from looking at the survey data that as manganese increased, we saw an increase in taste, odor, or color concerns about the water. And that's what this figure is showing on the right, where, for example, 16% of those with manganese below 100 micrograms per liter said they were somewhat or very concerned about the taste, odor, or color of their water, compared to 27% in the next higher bin, 100 to 300 micrograms per liter. And that goes up to 46% in the highest concentration bin. So one limitation of looking at this is that we did see a strong positive correlation between manganese and iron in these samples, and we know that iron imparts taste and staining issues at elevated levels. So we did look at that follow-up sampling that was done in a subset of households. 99 households participated, and looking at whether the water was still above our guidance value once it had gone through any treatment devices in the home. And we saw that in that follow-up sampling, 38% of the water that they were actually drinking in the home, 38% of the homes had manganese still above our health-based guidance value. And only 22% of those households mostly or always drink bottled water or get drinking water from another source. So we see that an elevated manganese concentration is not a complete deterrent to water consumption. Next slide. So I wanted to add this additional slide about the aesthetics because we recently did a talk on this to AWWA, American Waterworks Association, and attending that talk was Andrea Dietrich, who is a professor of civil and environmental engineering at Virginia Tech, and she'd actually done some studies looking at the aesthetics of manganese. And basically what she sent to us afterwards and communicated to us is that dissolved manganese, which is what is typical in the water here, is clear and colorless. And as soluble manganese, it's not imparting any staining or darkness to the water, and it has no taste. And in one study, the taste threshold for this dissolved manganese was determined to be 165,000 micrograms per liter. So people are not going to be noticing a taste. We do see that when it's in particulate form, it does impart a color to the water. So that's why we think in that Dakota County study that it was likely the iron that people were tasting and responding to rather than the manganese. So this was really useful information. I think there's still, Andrea pointed out that there's still a lot of confusion about aesthetics and people thinking that above the secondary MCL there's going to be a bad taste, but that's actually not the case. So next slide.
So now, hi, this is Helen. I'm going to talk about how we put sort of those pieces together and conducted a sort of a potential risk evaluation for formula-fed infants. So Deanna sort of mentioned our reference dose earlier. And I just wanted to give a little bit of background on what that is based on. So it's based on a laboratory animal study, but somewhat uniquely, this was based on neonatal rats. So very, very young animals were directly given manganese in water, which is a bit unusual because it's very difficult to dose those tiny little animals. But that is what was done in this study by Kern in 2010. And at every dose level that they looked at, they did see some level of effect. And our reference dose, for those maybe who aren't familiar with this terminology, represents a daily dose that, based on our current knowledge, is not expected to result in any adverse health effect. So the behavioral and learning abilities were observed after short-term exposure to these very young animals. And to address some of the uncertainties in that study, we applied a fairly large total uncertainty of 300. And that is to address the fact that we're extrapolating from neonatal rats to human infants. It's to address the variability we may see within the human population. And then also, because we did not, or that study did not identify a no effect level, there was also an additional factor added for that. So in addition to this single study, there was also a study that had been conducted in neonatal primates that also reported changes in activity patterns and behavior and sleep. So those findings also supported neurological effects that were observed in this study as well. And this reference dose of the 0.083 milligrams per kilogram per day, or 83 micrograms per kilogram per day, this is what was used as sort of the comparison benchmark for our risk assessment. So this is just to sort of step through how we went from that reference dose, which is the first step in our water guidance development. So again, that most sensitive health effect was seen in those neonatal animals. We applied that total uncertainty factor of 300 to add a margin of safety to the value. And then once we have that reference exposure level, we need to decide how much of that dose level are we going to allow to come from drinking water. And for formula-fed infants, we knew that formula contained manganese. And based on literature information that we had available at the time, we determined that we would only allow half of that reference dose to come from water, thereby allowing an equivalent amount or half to come from infant formula. We also used a high-end infant water intake rate, and the combination of these factors resulted in that 100 micrograms per liter as our current short drinking water guidance value for infants. Now, for our risk assessment, what we did was calculate the manganese exposure from formula itself and from water, so each of those separately, and then also combined. And then that exposure was compared to that reference dose. So we looked at a variety of scenarios. One that we looked at was taking sort of an average or mean concentration for the formula, and also sort of an average or mean infant intake rate. So not a high intake rate, but just an average intake rate. And we looked at water concentration. One was a median, which I'll present in this slide, and then the next slide will show how the combination with high-end water concentration turns out. So our median concentration is only at about 30 micrograms per liter. So that's, about threefold lower than our guidance value. So the contribution from formula is shown sort of in the orangish colors there. So for cow's milk, it's about 28%, soy is 64%, and amino acid formula is 122% of the reference dose. And an average infant intake of water at that median concentration would add about another 5%. So it's really only in this situation that amino acid formula that really rises above our reference dose. So we repeated this, again, using a mean formula concentration and a mean intake rate, but this time with the 95th percentile concentration, which is you know, almost 6 times higher than our guidance value. So the contribution from formula stays the same, but you can see now that intake of just of the water itself is at 92% of the reference dose by itself. So it's not surprising that when combined with the contribution from formula, there's exceedances of our reference dose at every combination of formula, different formula base. So we also did this looking at 95th percentile formula concentration and a 95th percentile infant water intake rate. So an infant drinking a lot of fluid and happened to be fed off one of the formulas that had those higher concentrations in. So again, we looked at that combined with the median water concentration. So you can see that the formula itself was virtually took up all of the reference dose, leaving virtually no room for additional contribution from water. Water alone contributed about 20% or 10%, I'm sorry, of the reference dose. So combined, we were just over for cow's milk formula up to almost getting close to 3-fold higher than the reference dose with the amino acid formula. And if we look at this with reconstituting, you know, formula with a 95th percentile water concentration, we get combinations that are anywhere from 3 up to getting close to 5 times higher MDH's reference dose. So each, so at that water concentration in particular, we're talking almost 2-fold the reference dose if you're at the 95th percentile water concentration for community water supply.
So we wanted to point out some of the limitations and uncertainties in our analyses. First, in the community water system analysis, some of the monitoring results might not reflect current manganese concentrations if there's been changes made to the system operations since the monitoring took place. We use the average result per system, and some systems might already try to manage aesthetic issues associated with manganese by limiting the pumping of those higher manganese wells. Not all system wells or intakes or entry points may have been sampled. An average result might not account for concentrations at the consumer tap due to pressure zones and mixing within a system. And we lack data for 46 small systems. Systems of this size were more likely to have elevated levels. We also did not look at private wells in our risk assessment, and 20% of our population is on private wells. And as I pointed out earlier, it's estimated that 50% of private wells may exceed our guidance value. What MDH has done is put out an educational brochure that's focused on well water in babies, and a picture of it is here on the slide. This is free to order. Anyone can order it and distribute it. We try to do some outreach around it. And in this brochure, we list the 5 contaminants that parents should test for before giving water to a baby or mixing the water with formula, and that includes manganese. Let's see, on the talk side, as Helen mentioned, the study that was used as the basis of the RFD, the lowest dose tested did result in effects, and we address this by applying an uncertainty factor of 3x. The World Health Organization recently put out a draft proposal for a guidance value for manganese in water, and they applied an uncertainty factor of 10. So there's going to be differences in how people try to address this deficiency if they base their water guidance value on the study. On the formula side, we had limited sample size. We only tested single lot numbers, and maybe these vary by lot number. We did 2 independent mixing events per formula, and these were done by 2 different people. And we just took the average between the 2. But you could get maybe different results, you know, when you have different people mixing the formula, and we did see that here. In terms of formula concentrations, there was a study that came out very recently as we were preparing our manuscript that reported even higher formula concentrations than our evaluation. They did test 2 amino acid-based formulas, and if you recall, the amino acid based formula was very high in our analysis. One was very high in their analysis, and one was lower. So we don't necessarily think every amino acid-based formula is extremely high in manganese, but we just don't have enough data to know. Another uncertainty is absorption differences that might exist between human infants and neonatal rats. It's possible human infants do have lower absorption than neonatal rats. However, Helen mentioned that neonatal primate study that also reported subtle neurological changes in neonates exposed to manganese levels that were less than 4-fold higher than our RFD. So it's likely that human infants and primates have similar absorption. So we still do have serious concerns, even with this uncertainty about absorption in human infants. Next slide. So in terms of our key takeaways, what we found was that community water system water concentrations commonly exceed health-based guidance. We do have a response plan to address this that I'll be discussing in the next slide. We found that concentration above guidance values is not a deterrent to drinking the water, especially with that new information that we learned from Andrea Dietrich. Formulas contain high levels of manganese, potentially leaving no room for contribution from any naturally occurring manganese in the water. And the issue is that, we have federal regulators, we have EPA regulating the water, we have FDA regulating the formula, and it's unclear whether they're talking to each other, but really they need to work together to try to address potential risks to formula-fed infants. So this might be a little challenging to do this cross-agency work to address this concern. Next slide. So as a result of all this information that has been coming out about manganese and with UCMAR results coming out, MDH Drinking Water Protection has been developing a response plan. And so first they're going back and resampling community water systems that they suspect as having elevated levels of manganese. And this began back in the third quarter of 2020. So they're starting with systems with higher manganese. The sampling is still ongoing and it's offered at no cost to systems. And I got a recent update from Todd Johnson. He's a district engineer supervisor in drinking water protection on how this plan is unfolding. So they've asked 224 public water systems to participate in the resampling. They've completed sampling at 58 systems. There's been 49 health risk advisory letters sent as a result. 15 systems that were invited to participate have opted out, chosen not to participate in the resampling. So if 2 rounds of sampling at these systems result in a concentration above our guidance value, the system does get this advisory letter. And depending on what the result is, it might have slightly different messaging. For example, if they're above 100 but below 300 micrograms per liter, the system is told that they're above the MDH short-term health-based guidance value for infants. Up to, if they're over 1,000 micrograms per liter, they are told they're above EPA's 1 and 10-day health advisory value. So when a letter is sent to a system, copies of a letter are also sent to district legislators and local public health to keep everybody in the loop. Next slide. So these health advisories that we are sending out to the systems are not enforceable standards. But we do communicate that we strongly recommend that the system take action to decrease exposure. And this might include changes in pumping practices, adding treatment or making modifications to existing treatment devices and techniques. And also we recommend public education and notifying customers. And there's been many meetings held now with public water system owners, city administrators, to try to explain the recommendations in the health advisory letter. In the health advisory letter. And MDH community public water system staff are providing technical assistance to the systems, and MDH toxicologists like Helen and Chris are responding to specific questions or concerns from city staff, citizens, or clinicians about health concerns. Next slide. So that's the end of our presentation. We did receive financial support to conduct some of the formula study and some of the work with Dakota County from Clean Water Funds. And we put our contact information here. If you have questions about manganese exposure in the risk assessment, please contact us, Deanna, Chris, or Helen. If you have questions about the manganese response plan, we invite you to reach out to Todd Johnson. There's his email there. Next slide. And if you want more details, you can find the Dakota County MDH private well study report on our website. It has quite a long link and it's a little hard to find, but these slides will be available to you if you want to find that link. And also you can access the article we published, Environmental Health Perspectives, and the link to that article is provided as well. So we are happy to take some questions. There's a little less time since we got a bit of a late start, but we're happy to take any questions.
All right, well, thank you for a very interesting and wonderful presentation. That was really a very interesting effort and so necessary. So I'm so glad we've got folks like you working on important issues like this. So it looks like there was a question that was answered. There was a question about if the companies were using the same method for testing. And it looks like, Chris, you addressed that question in the chat already.
Right. So, and basically we don't know because the FDA wouldn't let us compare what we measured with what the companies measured. So that was top secret information, and they wouldn't even, we asked, well, what if you just blacked out the names and we could just see if we were in the range of what the companies measured, and they wouldn't even do that for us. So we don't know how they measured it. We do know the FDA said that it's in the company's best interest to add a little more manganese into their formulas, because if it doesn't meet the minimum requirements, then their product can be pulled from the shelves. So we know they're adding more in than what's on the label.
And the companies may be, measuring it out based on mass. We did something more earthy, I guess, by having people actually mix it the way you would if you mix up a bottle for a baby. So we feel like our results are more reflective of what babies are actually consuming, since it was someone mixing it up according to the directions.
And then I see another question in here about the amino acid based formulas that were tested. And it looks like, Chris, you also already answered that one in the chat, that it was L-Care by Abbott Nutrition. And then I think we have a question here that is not addressed yet in the chat. Phil is wondering, are there any important differences in exposure considerations between the ionic states, manganese 2 versus manganese, oh man, is that it's a 4? No, that's 4, yeah, or 6. My Roman numerals are not up to speed on my Roman numerals, I guess.
Yeah, I know this really impacts how a system is addressing treatment for manganese. I'm wondering if Todd is on the meeting, if he wants to speak to this at all. in terms of treatment. In terms of exposure, I'm not sure. Todd, are you on?
Yeah. Can you hear me?
Yeah.
Yeah, I'm on. As far as treatment, most manganese in groundwater is in the dissolve stage. So the simple process to remove it is to oxidize it. But as far as exposure, I don't know. I mean, I guess that would be something on your end, Deanna, if there's a difference. But from a treatment standpoint, almost all of it in groundwater is in the dissolve stage. So
Yeah, because of that, we've just been assuming it's all dissolved manganese. So I don't know if it's in particulate form, how that impacts absorption or anything else on like the tox side. I'm not sure.
We do have another question on if you could talk more about the behavioral and learning problems that are associated with these higher manganese levels and what metrics were used.
Is that in terms of the toxicity studies or like epi studies?
Bonnie, if you want to clarify your question.
I was
That
just
would be-
curious. I just thought one of the slides said that there was the neurological problems were like more behavioral and learning disabilities, and I was wondering how you measured that. Like, was it like an infant score of how they're behaving, or like lower IQ scores as they got older? Or how did you determine those?
Deanna, did you want me to the
Yeah, why don't you
animal
talk
studies
about
or
from the animal side, animal tox side?
from the animal studies? And you have to remember these are neonatal animals, and well, just like human infants, also there are limitations with how you can test a really young animal. But with the laboratory animals, the types of things they notice, let's say for behavioral, is when you put an animal in a novel environment, there's a certain sort of typical behavior of exploration and sort of those sorts of things. So they saw changes in those types of behaviors. They also conducted, I think, a maze where they put food at the end of this maze. And so how long it took animals to learn how to discover the food was one way how they assessed learning abilities. And so on animals that at the higher doses had to do more trials in order to learn where to find that food.
Yeah, and on the
Nature.
epi side, they've looked at mainly school-age children. There hasn't been an easy way to do this for infants, and there's still not good understanding of what are the sensitive life stages that will result in these types of neurobehavioral effects. For example, is exposure prenatally important at all, or is it all postnatal? But the types of effects that are being reported in the epi studies include intellectual deficits like IQ, behavioral disinhibition, so different, more like ADHD type behaviors. So that's what they're really seeing on the epi side.
Great, thank you. So there is a couple of other questions. It looks like Chris over there is doing a great job of trying to respond to these questions in the chat so that everyone gets their questions answered. And she just she answered Sherry's question about testing the amino acid formulas, and it sounds like only one was tested. So there might be others that maybe are not as high in manganese, but the other question we had in there was about rule making, and if we would have to go to rule making to make these MCLs enforceable. It looks like Todd responded to that saying yes, rule making would be the route we go. And then Angela had a question here. If manganese exposure would be in the in the top 5 of neurotoxicant exposure to infants in Minnesota. So I think that's the only question in there that hasn't been answered is manganese in the top 5?
I guess it's depends on how you rank them too. I mean, obviously, manganese is needed. It's an essential nutrient at low levels. And so its potency is not the same as you would see with like something like lead. I mean, lead is still such a serious issue. So I'm not sure what do you think, Helen, in terms of trying to create a top 5 list of neurotoxic exposures to infants in Minnesota?
And I think we'd have to know more about what are typical infant exposures. I mean, maybe if you're talking about strictly only water, I don't know if the top 5, I mean, it might be in the top 10, but it would depend. We'd need to have more information, I think, to be able to answer that question.
Infants that are breastfed are getting very low levels of manganese, so it's really the formula-fed infants. Unfortunately, breastfeeding rates are not super high by 6 months. There's a lot of bottle feeding happening, but maybe within the first few months where we think infants are especially vulnerable, the breastfeeding rates are higher. So, but there will always be bottle-fed babies that we'll need to be concerned about.
Well, we are over our time here by a couple of minutes, so I do want to respect our speakers' time, and thanks everyone who was able to stick around for a little extended Q&A, and I'm glad everyone was able to join us this morning. And thank you again to all of you for sharing your work with us today. It was just a really great opportunity to learn about some of these really important issues that I think so many of us are all working on, and it's great to have this opportunity to share our work with each other so we can all be more knowledgeable and kind of help with where we can. So thank you for your time today and sharing your work with us.
Yeah, thanks much for your presentation. That was really an interesting talk and very insightful.
Thanks for
I'm
having us.
curious, just as
Thanks for having us.
one more question. You were talking about manganese throughout this study. Are there any, it makes me wonder if there are any other elements or contaminants that kind of fall into a similar concern where we're getting exposed naturally and getting concerned, through foods that raise similar red flags besides manganese, like arsenic, for example. Anything else on the radar screen out there that way?
Yeah, I think the origin of this formula study might shed some light on that if you want to talk about how this formula study came around.
Yeah, so it actually started by looking at boron. We needed to know how much boron was in infant formula because that's something that is in the soil. It's weathered, it gets into our water. It also goes into the food we eat. And so it initially started with us having this data gap of knowing how much boron infants are exposed to. And while we were working on that, we were allowed to add in some additional elements to look at. And then manganese happened to be, we knew that we had also made guidance values based on how much we thought infants were receiving. So we wanted to double check that and then found that they're actually getting a pretty high dose of manganese just from infant formula.
So I think the formula makers are trying to look into keeping arsenic out of the formula. But there are certainly other naturally occurring elements that they're getting from formula and water, and getting a dose that may be excessive between the two. And one example might be boron.
Great, thanks. Just had to ask. Very insightful.
Arsenic in baby foods is another story.
Yeah.
It's been in the news quite a bit.
Well, that falls outside the purview of a water issues talk, I'm afraid, but equally concerning, I guess. Well, thanks everyone for the presentation and for listening in.